By the end of this chapter, students should be able to state and describe Kirchhoff rules. Students also should be able to use the Kirchhoff rules to solve circuit problems. In previous chapter, we already learned how to use Ohm's law to solve circuit problem. But for more complex or circuit with multiple branches and elements, we cannot use Ohm's law anymore. We have to use Kirchhoff rules to solve this kind of circuit problem. For example, like this circuit, we have multiple loops here and multiple battery. So Ohm's law is not applicable for this type of circuit.
First of all, we need to understand what is the junction itself. For example, the circuit, we have two different battery, and the junction for this particular circuit is a point which the current split into different current. For example, the current from battery I2 is split out into I1 and I3, and the current I1 and I3 will combine together into I2 again. Okay, the point A and C is called as junction.
Kirchhoff has two rules. Okay, the first one is Kirchhoff junction rule or Kirchhoff current rule. Kirchhoff first rule states that the total current that enter any junction will equal to total current out from that junction. Okay, so let's say we have this type of circuit. We choose one junction, for example, junction A. Okay, if the current flow from battery number 1, okay, flow from positive, enter the junction A. So the first current we label as I2. Okay, I2 enter the junction A. Okay, from the junction A, the current flow out into two different paths. The first path, the upward one is I1 and the downward one is I3. So we equate in the equation the total current in, which is I2, equal to the total current out, which is I1 plus I3.
Next, we have to understand what is loop. Okay, in this circuit, we can produce three different loops. Loop is the sequence of consideration. You can choose either to the direction in clockwise or anti-clockwise. For example, the loop number 1 can be in clockwise direction. Okay, the second one will be in anti-clockwise direction, and the third one is in clockwise direction.
Okay, for the Kirchhoff second rules, which also known as loop rules or voltage rules. In these rules, it states that in any loop, the sum of EMF is equal to the sum of the products of current and resistance. Okay, in simplified version, we can write down like this lah, formula. Okay, for example, in the previous video, we know that in this circuit, we can have three different loops. To apply these second rules, we need to choose loops by loops lah. For example, if we want to apply Kirchhoff second rules for loop number 1, the first loop. Okay, in this loop, for example, loop number 1, we can label loop number 1 as L1. Okay, the direction for loop number 1 is clockwise direction. Okay, why? Because we follow the direction of current from EMF number 1 to make us easy to calculate lah. Okay, if we follow the direction of current in the battery, for example, the current I2 from battery number 1, okay, so our direction will be same direction as the current. Alright, so loop number 1, we want to apply the second rules in this particular loops. How? In this loop, we have one EMF. Okay, in loop number 1, we total the EMF in this loop. For example, in this loop, we have EMF 1 only. So, we equate to the current, the total product of current and resistance. So, in this loop, we have R1 and R2. Okay, based on the video, we know that we already label the current from junction A and B. In this particular junction, the current is I2. Okay, from junction A outward, we label as I1. Alright, so I1 is entering the resistor number 1. So I1 acting on resistor number 1. But for R2, I2 will be acting on R number 2. So we just add up all this product of I and R. But in this example, the direction is equal. So both of resistor will produce positive sign. Okay, after this we will study more how to put the sign convention for this product. Okay, to assign the sign convention for EMF in the second Kirchhoff law, we have to consider the direction of current inside the battery. For example, this battery, the current inside the battery is directed toward right. Okay, because the current flow outward from positive to negative pole. But inside the battery, we label the current inside the battery is from negative to positive. Okay, this one we call as current in battery or current in EMF. Okay, if the direction of loop equal to the direction of current in battery, we should label the EMF as positive direction. Okay, but if the current is in battery oppose the direction of loop, for example, direction of loop toward right, the direction of current in the battery toward left, so our EMF will be negative sign. For product of IR, product of current and resistance, we have to compare the direction of current inside the resistor. For example, we label, let's say, the current flow in the resistor toward right. We compare the direction of current in the resistor with the direction of loop. If the direction is same, we will get the positive sign. Okay, we assign the IR with positive sign. If the direction of current inside resistor oppose the direction of loop, we assign the product of IR with negative sign. Okay, for example, we choose loop flow in the circuit. Okay, we choose the bottom one. So in the bottom one, we will apply Kirchhoff second law. Okay, Kirchhoff second law state that the total EMF equal to the total product of current and resistance. Okay, for example, we choose loop the below one. Okay, so we label the loop direction. For example, we choose the direction in anti-clockwise. So this one we call as loop number 2. So in loop number 2, we can apply Kirchhoff second law. Okay, loop number 2 is directed anti-clockwise. So the loop flow in anti-clockwise direction. Okay, then what we need to do, we have to clearly state the direction of current inside the battery. For example, this EMF number 1, the current flow from positive outward, but the current flow inside the EMF is directed toward left. Okay, from negative to positive. Same as the EMF number 2. The current inside the battery is directed from negative to positive pole. Okay, so we total the EMF in the loop. So in loop number 2, we have two EMF. EMF number 1 and EMF number 2. Okay, but the problem is how to determine the sign for this EMF. Okay, let's compare the direction. The direction of loop is flowing. We can say that the direction of loop is in anti-clockwise direction. So if we compare the direction of EMF number 1 and the direction of loop, we can say that the direction is same. So EMF number 1 will be positive direction. Okay, we assign positive because the direction is same. And what happened to EMF 2? If we compare the direction of EMF 2 and the loop, also same. So we put positive sign convention for EMF number 2. This is how we apply the sign convention for EMF. Okay, let's see what happened to the resistor. Okay, the resistor, okay, the current flow in resistor is depend on our label. Okay, for example, we label current number 1. Okay, current number 1, we label in the first Kirchhoff law. Okay, let's say current number 1, current number 2, current number 3. Okay, the current number 1 will affect the resistor number 2. Okay, the same current flowing from EMF 1 is current number 1, and the same current also flow in resistor 2. Okay, so if our loop is in anti-clockwise direction, so just like before, just like we do in EMF, okay, the current flow, we compare the direction of current flow and the loop. Okay, for example, for R1, for R2, the current I1 flowing in the same direction of loop. So our R1, R2 the current flow inside the R2 is I1. So the current is positive direction. Okay. So this is how we assign the sign convention for IR. Okay. In this loop, we have three different resistors. We have to add R3. Okay, for R3, the current flow inside the R3 is I2. I2 flowing into R3. This one I2. I2 is toward right, and the loop also toward right. Okay, the loop is in anti-clockwise. So at R3, the loop is in toward right direction, same as I2. So our I2 will be positive. Okay, the addition here is due to the summation, and the symbol positive is due to the sign convention that we assign to this current. Okay, the last one, we add up R4. Same as I3, the current flow is I2. So I2 is positive because it is same direction with the loop. So we already assigned all the product of I and R with correct sign convention. Okay. Okay, if we have the problem involving Kirchhoff rules, there are several steps that can we follow to ensure that we can solve the problem. Okay, for the first step, we have to choose and label the current at each junction. Second step, we apply the Kirchhoff first law at the junction. Third step, we choose any loops, one or two closed loop, depend on the question. Okay, and apply the second law for each loop. Last one, we will need to solve the simultaneous equation normally, depending on the question and the variable that asked in the question. Okay, in subtopic 3.7, electrical energy and power, we will learn two different physical quantity. The first one is electrical power, which the formula is P equal to IV, the product of current and voltage. This one is the general formula for power. Okay, or also known as power supply. Okay. Another type of formula for power is P equal to I squared R and P equal to V squared R. Okay, these two is known as power loss, power consumption. Okay. Then we will learn the electrical energy, W. Okay, W is electrical energy. Okay, first, what is electrical energy? Okay, if we look at this figure, we have a potential different battery, EMF. Okay, the current flow from positive to negative pole. Okay, through an electrical device. Okay, in this electrical device, we have 2 points, A and B. Okay, then what is electrical energy? Referring to this figure, electrical energy is the energy to carry charge Q from B to A. Okay, the energy to bring, let's say, we have charge from A, and let's say we have 3 electrons, for example. We want to bring electron or proton lah, positive charge, from A to B. So what is the energy required to make this happen? Okay, this is what electrical energy supply mean? Okay, the energy to bring or the work done to bring charge Q from B to A. Okay, from previous lesson you already know that in chapter 1 work or electric potential V is equal to work over Q. Okay, this is from chapter 1 electrostatic. Okay, then from this definition, work is energy required to bring charge from A to B due to potential. By definition, the power with symbol P is defined as the energy liberated per unit time in the electrical device. Okay, this is the general definition for power. Okay, for example, an electrical power which supply an electrical device is given as power supply equal to energy per time. Okay, power, the general equation for power is energy over time. So if the energy is in electrical energy, so we substitute energy with electrical energy W. Okay, we substitute the formula of energy, so we can simplify the formula as P equal to IV. Okay, this one is electrical power supply. Okay, for example, if we have a battery and a resistor, okay, the battery will have the value of potential difference V, for example 3 volt, and the current flow may be 1 ampere. So the electrical supply from battery equal to IV 1 multiplied by 3. So we have 3 watt. Okay, the unit for power is watt. Next, we want to understand the power across resistor, or known as power loss. Okay, in this slide, we already showed here there are two different formula that is related to power equal to IV. Okay, but how to use these two formula? These two formula is to measure specifically the power loss across resistor. Okay, the power loss into heat across resistor. So we cannot use power equal to IV to measure the power loss. Okay, how we get these two formula? We just combine power equal to IV with Ohm's law. So the first one, we have power loss in terms of I and R. Another one, we have power loss in terms of voltage and resistor. So what is power loss itself? For example, if we have a battery or potential difference connected to a resistor, maybe the power supply from this battery, maybe the power supply equal to 3 watt, but the power loss might be different from the power supply, maybe 2.5 watt. Okay, they are different in terms of efficiency, maybe. Okay, not all power are used up efficiently in this resistor. So we have to calculate specifically what is power loss on that resistor. Okay, by using the current on the resistor. For example, we have the current, we multiply, we square and multiply by the value of resistor, or we have this formula, voltage R squared over R. Okay, this is quite different with, from voltage supply. Okay, voltage supply may be value 3 volt, but the voltage across R is measured directly onto the resistor. So VR is different with V supply. Okay, VR is measured directly on the resistor. Okay, so the formula must be used with correct value. Okay, so the power loss or power across resistor is a scalar quantity, and it's same unit as from previous one. Unit for power is watt. Okay, from this formula we also can measure electrical energy supply into heat, which also refer to energy specifically released on the resistor. So if we want to use this formula, we must make sure that the voltage is measured directly on resistor R. Okay, in this subtopic, we will explain to you the principle of potential divider and how to use the equation of potential divider. Okay, what is potential divider? Potential divider is a method to divide the voltage supply. Okay, for example, if you have a very big, large value of voltage, 100 volt battery, so you don't want to use all these 100 volt. For example, maybe a light bulb cannot withstand 100 volt, so you need to divide it into smaller value. Okay, so we will have to connect this battery into maybe this one we have two different resistor. So if the resistor have the same value, for example 2 ohms, and the resistor 2 also 2 ohms, so the voltage across resistor 1, if we put a voltmeter like this, V1, we put voltmeter and measure the voltage across resistor number 1, the voltage will be divided evenly. Okay, V1 will be equal to 50 volt and V2 also equal to 50 volt. If you change the value of the resistor here, let's say 3 ohms and another one also 3 ohms, the value also the value for voltage still same. Okay, voltage equal to 50 volt, V2 also 50 volt. So if the value of resistor equal or same, the voltage will be divided evenly. What happen if the value is different? For example, R1 is 3, R2 is 1 ohms. Okay, so the division will produce uneven fraction. Okay, V1 will be equal to, okay, the larger the resistor, the voltage will be also large. Okay, so the 3 ohms will produce 75 volt. Okay, then the V2 will be 25 volt. Okay, so how we can calculate this 75 volt? This is due to this formula lah, or logically you can just divide into percentage lah, 3/4, so it is 75% from 100 volt. Okay, this is the concept lah. Okay, by this formula explain what I told you, 75% from 100 volt. Okay, R1 is, for example, 3, R1 3 plus 1, so 3/4 multiplied by 100 equal to 75 volt. Okay, so it is just a matter of ratio and percentage lah. Alright, the resistor R1 and resistor R2 can be replaced with a uniform homogeneous wire. Okay, uniform homogeneous wire is labeled as ACB. Okay, this is a wire not an ordinary wire, but a wire with resistor R. Okay, this wire have resistance. Okay, ordinary wire didn't have resistance. Okay, so the wire with resistance also can divide the voltage. For example, voltage 100 volt also. Okay, the voltage across a particular length, for example V1, can be calculated by making the ratio of the length. Okay, for example, length 1 20, length 2 80 centimeter. Okay, so the ratio of length 20 divided by total length, which is 20 plus 80 centimeter. Okay, centimeter cancel. Okay, multiply by 100 volt. So the voltage 1 is equal to 20 divided by 100 multiplied by 100. So the voltage is 20 volt. Okay, this example can be simplified or can be shown into these two formula. To calculate V1, we just ratio the length onto the length total and multiply by the voltage supply. So V is supply voltage. So not only we can divide the voltage by using resistor, but we also can divide the voltage using a long homogeneous wire with resistance. Okay. In this topic, we will explain to you the principle of potentiometer and its application, and we will use the related equation for potentiometer. And the last one will be covered in the experiment 3 to determine the internal resistance R of dry cell using potentiometer. Okay, what is potentiometer? Potentiometer is a circuit that is consists one driver cell or accumulator, a battery or power supply that is connected to a long straight 1 meter constant wire. Okay, we are not using normal wire, but we use constant wire which have its own resistance. Okay, this is not a normal wire. This wire is having its own resistance. Okay, then the wire at one point of the wire, the point A, is connected to any EMF or unknown EMF or unknown battery. Okay, for example, when we found unknown battery, then we want to measure what is the value for the EMF. That unknown battery we attach in between point A and a galvanometer. Galvanometer just like the ammeter, but it measured very small current. Okay, this is a device that measure very small current. Okay, to detect. Okay, basically it used to just to detect the small current to ensure that is there any current flow in the circuit. Then at another point of galvanometer, we attach a jockey. Jockey is simply a metal rod that slide across A and B. We slide the jockey across A and B. Okay, what is the function of this potentiometer? Okay, there are three functions. The first one is to measure unknown EMF. Another one to compare EMF. And the last one is to measure internal resistance. Okay, this is three application of potentiometer in our syllabus. Okay, what happened when we attach an unknown battery? Not the dead one lah. We must make sure that this battery is still having a potential difference or its own EMF. So when we attach this unknown EMF here, okay, then we slide the jockey. We slide across A toward B. Then if the galvanometer show value of 0, which means no current through the galvanometer, so in this particular point we measure the length across AC, the value of length AC. By having this value, we can determine the voltage here. Okay, how? Okay, when the galvanometer show value of 0, okay, that means Vx equal to VAC. This is the concept. Okay, in this diagram, we can say that the voltage across the EMF Vx is equal to VAC. Okay, when these two is same value, that's why the galvanometer show 0 reading. Okay, then how to calculate the voltage across EMF X? Okay, voltage across X equal to EMF unknown lah, unknown EMF. Okay, Vx equal to VAC. Okay, from previous lesson, we already learned about voltage divider. Okay, so the concept is the same. We just make the ratio of length across AC divide by the total length, which the potentiometer, the length of AB, normally we use 1 meter. Okay, it's already planned that the length of AB must be 1 meter. So normally we put 1 meter lah, but if the value of AB different, so we just put length AB. Okay, we just ratio length AC toward the total length, which is AB, and multiply by the voltage from accumulator, V driver ni. Okay, driver or accumulator. So the formula is same, just like the potential divider. Okay, we also can compare two different EMF of cells. Okay, the arrangement is just like this. Okay, the difference is we have two EMF connected. Okay, but actually this is not two EMF connected simultaneously. Okay, not connected both in the same time. Okay, the switch can be alternate from number 1 and then can be alternate to point number 2. So this arrangement just not makes any difference compared to the previous one. Okay, just we put different battery in this point. Okay, what happened here? The first step, we put the EMF number 1, then the switch is set to point number 1. That means the current flow from the battery, okay, the current flow only flow through battery number 1. The battery number 2 can be ignored in this step. Okay, what happened? Then we slide the jockey and get the first reading. length number 1. Okay, let's say length number 1 equal to 40 centimeter. Okay, then we switch the switch from galvanometer to point number 2. That means the current only flow in battery number 2. So what happened? Okay, length 1, 40. Okay, what happened after we switch to point number 2? We slide the jockey and get the second reading. For example, length 2 equal to 60 centimeter. Then we can compare the value of EMF number 2 and EMF number 1 by substituting the value of length number 1, for example 40 centimeter divided by 60 centimeter. So our ratio of EMF number 1 and EMF number 2 is 2/3. This is to just to compare two different EMF. But if you already know the value, for example EMF number 2, you already know the value of EMF number 2, let's say 3 volt, then you can find the value of EMF. 2/3 multiplied by 3 volt. So this is just a matter of ratio. Okay, in potentiometer we just ratio the value and compare to the length, same as in the potential divider. Okay,